little or no electron flow occur. So, in the neon, in the valence orbit, no free electron is available because the valence orbit is completely filled. Next is energy band theory. In an atoms, electrons revolve in different orbit possesses certain energy levels. The amount of energy on each orbit is fixed, but when we talk about the solid where the atoms are closely packed, the electron on the various orbit are influenced by the energy of electron of neighboring orbit. In that case, energies of various band are considered in a single band. So, depending upon the number of orbit, the energy level of the electrons is different in different orbit. So, according to energy level, we have formed the energy band. So, in the first energy level, the electrons of same energy will reside in second energy level, energy of another level will reside, and so on. So, the range of energy possessed by various electrons of the same orbit of different atom in a solid is known as energy band. So, the range of the energy possessed by various electrons, various ਜਿਹੜੇ electrons ਨੇ ਉਹਨਾਂ ਦੀ ਜਿਹੜੀ range ਹੈ ਉਸ range ਨੂੰ ਆਪਾਂ ਇੱਕ band ਦੇ ਵਿੱਚ show ਕਰਾਂਗੇ. So, the range of energy possessed by the various electron of the same orbit of different atom in a solid is known as energy band. So, there are three main types of band, two main types of band, valence band and conduction band. If you see in this diagram, the last band is called valence band. So, the energy possessed by these electrons which are revolving in the valence band, the range of energy possessed by these electrons are considered in valence band. So, the range of energy possessed by valence electron, that is electron present in the outermost orbit, is called valence band. This band may be completely or partially filled by valence electron. Second is conduction band. The range of energy possessed by free electrons, those electrons which are responsible for the current conduction. Valence band, valence electron can make free when we supply energy to the valence electron. After getting energy, the valence electron become free, and those free electrons, the energy of those free electrons, the range of energy possessed by free electron is called the conduction band. The conduction in solid is possible only when some electrons are present in the conduction band. Next is energy gap. The gap between valence band and conduction band is called forbidden energy gap. So, classification of material on the basis of energy band. Material can be classified on the basis of energy band. First is insulator. In insulator are those material in which we cannot pass the electric current easily. In insulator, conduction band remain empty while valence band has many electrons. In this case, forbidden energy gap between the valence band and conduction band is quite large, approximately 20 electron-volt. So, main difference is the main point for the classification of material on the basis of energy band is the forbidden energy gap. Higher the energy gap, lesser will be the conduction. So, if you see the gap between the valence band and conduction band, that is the energy required for the valence electron to lift to the conduction band is very high. Energy required is approximately 20 electrical volt. So, higher energy required for the valence electron to become the free for the current conduction. Second is semiconductor. In semiconductor material, those material whose resistivity lies between conductor and insulator. In semiconductor, valence band is full of electron while conduction band is empty. This is the same case of insulator, but the difference is the energy required to lift the valence electron to conduction band is small. So it required some energy, but the energy level is small. So 1 electrical volt is sufficient to lift the valence electron to the conduction band. So semiconductor material act like a insulator in a normal condition, but when we supply energy more than 1 electrical volt, then it act like a conductor. Next is conductor. Conductor are those materials which offer least resistance to the electric current. Here conduction band is overlapped with valence band, so large number of electrons can jump from valence band to conduction band with the application of some small potential difference. If you compare semiconductor, it required some energy to lift the valence electron to the conduction band, but in the conductor, valence band and conduction band both are overlapped, so very small energy is required to lift the valence electron from valence band to conduction band. So all the valence electron which are present in the valence band are available for the current conduction in the case of conductor. That's why conductor offer the least resistance. Now semiconductor again, what is semiconductor? The material whose resistivity lies between the conductor and insulator, or you can say the whose conductivity lies between the insulator and the conductor. Silicon and germanium, as already discussed, are the main material semiconductor materials. Both have 4 valence electrons in their outermost orbit. To fill the outermost shell orbit, each atom acquire 4 more electrons by sharing 1 electron each from the 4 adjacent atoms, and hence form the crystal. So each atom has tendency to fill its last orbit. So silicon and germanium has 4 valence electron, and it complete its last orbit by sharing 4 electron from the neighboring electrons. So in the diagram you can see that this silicon electron has 4 valence electron, and it complete its last orbit by sharing 1 electron from neighboring electrons. So it shared 1 electron from this neighboring atom, silicon atoms, and here second sharing, here is third, and here is the fourth sharing, and it completes its outermost orbit with the 8 electrons, and this bonding is called covalent bonding. In a crystal, the atoms are bonded together in a cohesive manner. In the figure, the core represents the nucleus and all other electrons as valence electrons. The valence electron takes part in forming covalent bond with the 4 neighboring atoms. At absolute zero, all 4 covalent bonds are intact and no electron is free to conduct. First semiconductor material is germanium. Germanium is an earth element. Pure germanium is obtained from coal ash in the form of germanium dioxide, which is then reduced to pure germanium. Atomic structure of germanium we already discussed. It has 32 electrons, so 2, 8, 18, and last orbit has 4 electrons. It follows the same formula, 2n square. 2n square in the first orbit, 2 1 square 2, second orbit 2 2 square 8, and third orbit 2 3 square 18s, and in the last orbit maximum of 8 electrons can reside, but here 4 electron that is valence electron, will reside in the last orbit, because 2, 8, 18 is 28 plus 4, 32. 32 is the atomic number of germanium. Next is crystal structure. A substance in which the atoms or molecules are arranged in an orderly pattern is known as crystal. All semiconductors have crystalline structure. Each atom is surrounded by neighboring atom in a repetitive manner. Therefore, in a germanium crystal, a large number of atoms are bonded together. This bonding is due to the fact that each atom has tendency to complete its outermost or valence orbit by acquiring 8 electrons. However, in most of the substance, the last orbit is incomplete, that is last orbit does not have 8 electrons. So, this animation is showing the covalent bonding. Germanium atom complete its last orbit, that is it requires 4 more electrons by sharing with the neighboring electrons. So, for this germanium atom complete its last valence band by sharing the electron with the 4 neighboring atoms. Germanium is sharing 1 electron with this with this neighboring atoms, 1 with this, and 1 with this, and 1 with this, and it completes its 4 valence and it completes its valency of last orbit. Same way, this germanium atom share 1 with this, 1 with this, 1 with this, and 1 with this, and in this manner all the germanium atoms share with the neighboring atom and form the structure known as crystal structure. This structure is called crystal structure, and this bonding is called covalent bonding. Same way, silicon atomic number is 14, and valence electron is in the last orbit is 4, and the same way it form the covalent bonding, and in the last orbit the vacancy of 4 is completed by forming the covalent bonding with the neighboring silicon atoms. Next is concept of electrons and hole. At absolute 0, the valence band in the intrinsic semiconductor is totally filled and the conduction band is empty. So, whenever the covalent bonding breaks, 1 electron will got free for conductions, and the valency and the vacancy from where electron got free is called the hole. This electron jumped from this covalent bonding after breaking this covalent bonding, and the vacancy left behind is known as hole. Intrinsic semiconductor. An extremely pure semiconductor is called intrinsic semiconductor. So, the semiconductor material that we discuss all are intrinsic semiconductor having no impurity atoms. And next is extrinsic semiconductor. The semiconductor when doped with the impurity atoms is known as extrinsic semiconductor. A semiconductor to which an impurity at control rate is added to make it conductive is known as extrinsic semiconductor. So, doping is the process of adding the impurity atom. There are 2 types of impurity we can add. First is trivalent impurity, second is pentavalent impurity. When we add trivalent impurity, then the one neighboring atoms left without covalent bonding, and there form the hole. When we add pentavalent impurity, then pentavalent impurity has 5 valence electrons, 4 of them form the covalent bonding with the neighboring atoms, and 1 electron will got is extra, which is not from any covalent bonding. So, in pentavalent, when we add pentavalent impurity, then we have 1 extra electron, and when we add trivalent impurity, then we have one shortage of electron, and they form the hole. So when we add pentavalent impurity, the semiconductor form is known as n-type extrinsic semiconductor. You can see when we add arsenic atoms, that is pentavalent impurity, then 4 of electrons form the covalent bonding with the neighboring atoms, and one of the atom of arsenic atoms, one of the electron of arsenic atoms does not form the covalent bonding with any atoms. So this is extra electrons and is used for current conduction. In p-type semiconductor, trivalent impurity is added, and trivalent impurity has 3 valence electron. So 3 electron will form the covalent bonding, and one neighboring atom will left without covalent bonding, and the space is this space is called hole. Thank you.